Okay, thank you very much, Barry. Hi, everyone. Thank you for joining this webinar. I guess I switch off my camera now to be on the safe side with the bandwidth too. So I'm, let's say, co-founder of Phenaris, a spin-off of the University of Vienna, and actually I'm also professor of pharmacoinformatics at the University of Vienna. And what I would like to give you today is an overview on the tools we are offering. It's collaboration between the university group and the company, and related to toxicity, so the work we are doing in EU-ToxRisk. And this is, when we look on the portfolio of Phenaris, it's currently three pillars. It's transporter informatics, which I will focus on mainly today. It's toxicological read-across, safety assessment. I just will give you a very few glimpses what we are offering here. What I will not talk today about is modeling of on and off kinetics, which we also did in light of another IMI project, but this is not related to toxicity yet. So when it comes to transporters, I guess you are very well aware that we have around 500 transporters in our genome. It's 48 ABC transporters. They are mainly efflux transporters, and it's 460 SLC transporters. They are dominantly inward transporters, but some of them are also efflux transporters. And then you see here in the picture from a review of Nature Reviews Drug Discovery, the multiple role these transporters have. For example, when you look here on the hepatocyte and you look on bile acid homeostasis, so NTCP is transporting bile acids from the blood to the hepatocyte, BSEP is transporting bile acids from the hepatocyte to the bile duct, and ASBT is uptaking bile acids from the gut back to the blood flow. And then these three, so there are three transporters involved, for example, in bile acid transport and homeostasis. And when you block, for example, here, when you have a compound blocking BSEP, you get a risk of accumulation of bile acids, and which might lead to cholestasis. And this is why transporters are not only related to ADME, they are also related to toxicity. And FDA asks you for testing at least the following 6 transporters if you would like to register a drug. So in the university group, we are in transporters, mainly in ABC transporters. We started almost 30 years ago. Very conventional QSAR studies, Hunch analysis, doing correlation, P-glycoprotein inhibitors, correlations, physicochemical properties like log P versus biological activity, drawing our conclusions from this sort of QSAR analysis, designing the next compounds, testing them, doing again models, drawing conclusions. So, for example, we were able, just starting with a P-glycoprotein inhibitor with an IC50 of 3 micromolar during QSAR to get it down to 3 to 4 nanomolar. So that's very conventional. We do that permanently. It's still ongoing research in my group. With the first structures of ABC transporters coming out, we also included a structure-based design. Here you see a docking pose of one of the proper phenotype inhibitors in a homology model of the human P-glycoprotein, explaining very well the SAR we see in the conventional Hunch analysis. So how do we validate models like this? We always do a prospective validation. That means basically, for example, in this case, we transform this docking pose to a structure-based pharmacophore model. We screen a compound library, we order the top-ranked hits, and we test them to get a proof that we are also able to make predictions, which at the end of the day are valid and allow us to identify new inhibitors. What you see here is also a structure-based classification. So using the experience we have, docking a set of almost 2,000 compounds, P-glycoprotein inhibitors, just rigid docking, taking the top scored pose, and having the scoring values of the inhibitors and having the scoring values of the non-inhibitors. And when you take the intersection point here, when you take this as threshold for classification, you get a quite decent classification model. It's not as good as the machine learning models we have, which I will present shortly, but it still shows sort of an acceptable statistical performance. Here you see another example, that's the bile salt export pump, where we use data from provided by AstraZeneca. We also extracted data from drug bank, so we made, in that case, a random forest model, then screened drug bank for identifying compounds and ordering them, testing them, and in that case, we identified, for example, bromocriptine as being a BSEP inhibitor, which was up to this study not known yet. What you see here on the right side is, let's say, even a step forward in the docking-based classification. Here we took this data set from AstraZeneca into a homology model of BSEP, and we extracted the ligand protein interaction fingerprints. So basically, what you see here is a heat map of substructures of ligands and amino acids and interactions. And these are first attempts to somehow identify, specify crucial amino acids which are interacting with ligands and partial structures, substructural moieties of ligands interacting mainly with the protein. So these are the studies we are mainly doing in the university group, and they are of course continuing. We have a permanent interest in transporters. Currently, we are doing a lot of stuff on SLC transporters, SLC6 family, SLC10 family. So also there in an EU project, we combine ligand and structure-based design. So what about now models? When we started doing machine learning and when we started to extract larger data sets out of literature using KNIME workflows, for example, we also started to develop classification models. So what you here see is a set of classification models for inhibitors and substrates of a set of transporters. You see here BSEP, PGP, MRP2, MRP3, MRP4, BCRP, OATP1B1, OATP1B3. And we make these models available via a web service of our university group. It's a very lightweighted tool. You draw a structure, you select which models you would like to get prediction from, and you get the sort of fingerprint, positive, negative. So it's classification, yes or no. This service is free of charge because, of course, we receive also funding from the European Union, so we give back to the community our developments. So you can access it via LiberTalks, Univia, CAT. But in parallel, we also develop, and that brings me to the company, we develop, let's say, more elaborated, more in-depth models for a subset of transporters, which we provide via the company and which are available upon request and different license models. In that case, we currently have 6 models for 6 transporters. Why not all the ones we have on the university website? On the university website, we also have a set of substrate models, but there the performance is not as good as for the inhibitor models because the underlying data sets are not that robust than those for the inhibitor models. It's always the question, when do you consider a compound to be a substrate or not a substrate? It's not so easy to define. For example, in ABC transporters, the inhibitors, most of the inhibitors are substrates. They are just diffusing back and blocking the pump by keeping the pump busy. So there are different, on a molecular level, there are different possibilities why a compound might be a substrate on a molecular basis or on a, let's say, cellular basis, whether you have net transport or not. So in Phenaris, we focused on inhibitor models for 6 transporters. In addition, it's not just one classifier. We offer 3 classifiers. So we offer support vector classification, random forest classification, and k-nearest neighbor classification. So the interface is more or less analogous. You draw a structure, then you select the transporters you would like to be predicted. And when you press the submit button, you finally get the heat map. It's interactive, so it's taking you a few seconds, and you get the results here in a color coding, which means red, orange, green. What does this mean? As it's classification models, we get an output between 0 and 1. So we decided from 0 to 0.35, it's, let's say, a non-inhibitor, so it's green. From 0.35 to 0.65, we wouldn't really say, so we keep it orange. So it's somehow in between, you know, the closer you go to 0.5, the more uncertain your prediction is. And if it's above 0.65 to 1, it's red. So we have here, and you see in some of the models, in most of the models, you have consensus, not in all models. We actually provide you the results of all 3 classification models we are running behind to provide you also with a choice. If you see that, for example, you have internal data and your compounds, for your compounds, for the ones you know your inhibitor profile, the random forest classifier is closest to your experimental data. Maybe you just make predictions with the random forest classifier because these might be most close to the applicability domain of your compounds, of your data set. So you can do that interactively. You change the structure, you do the prediction again, you change the structure, you do the prediction again. Here you see, finally, after a few minutes, you can collect a full heat map. Here you see, for example, the last compound is the carboxylic acid. And here you see that, for example, in that case, in case of PGP, it becomes a non-inhibitor. And we know when introducing a negative charge, you most probably kill PGP affinity. So this is what you get with the transporter models. Of course, we also implemented applicability domains. So for each model, we have an applicability domain based on a local density model. So you can, when you click here, this window opens, you see the structure. You can select which of the transporters you would like to be displayed, and you see then it's in domain or it's out of domain. And when you click on these graphics, you see where the compound based on the applicability domain would be located. This is the interactive mode. What you also can do with the Phenaris interface, which is not possible in the university interfaces, you upload an SDF file, you start a prediction in the background, and you get a notification when the prediction is finished. And then again, you can display the full heat map, so you can do a batch execution. You just upload an SDF file with the structures, and you can download a CSV file with all the predictions, so with the transporter interaction, fingerprint predictions. So these are the transporter models we are offering via Phenaris. Of course, we are also offering services. So if you would like to have it more customized, so we definitely could provide predictions for substrate properties, especially if you also have data, but currently we would not offer the models just for use because they need a deeper analysis and a more elaborated reporting, I would say. We can customize our models for your in-house data sets if you provide us with your data, of course, under secrecy agreement conditions. We can develop models for your transport of interest. We can perform large-scale predictions. So what we did already was for one customer, he was asking us for 4,000 compounds. So in that case, it was just one shot. So we retrieved the compounds, we made the cleanup of the structures, we did the predictions, we provided a report. And we can also of course, combine the structure-based models I showed you, for example, in talking to PGP, talking to BSEP. We are currently talking to the BCRP structure, which came out 2 years ago. We combine structure-based models with the ligand-based ones to, in a lead series, give you real insights. Where are the crucial parts in your structure? If you need to design out, for example, PGP properties, or you would like to design in BCRP properties. When it comes to toxicity, what we also did is we tried to combine machine learning models, based models for hepatotoxic endpoints with the predicted transport interaction fingerprints. So that's published in several publications. That was mainly the thesis of Eleni Kotsampasako. What we did here is we compiled data sets for DILI, for hyperbilirubinemia, for cholestasis. We made machine learning models for predicting DILI plus, DILI minus, based on a standard, let's say, on descriptors and doing random forest or support vector classification of one of these classification algorithms. And then we added as additional descriptors, as information, the predicted transporter interaction pattern. And then we compared the models with or without the predicted transporter interaction patterns. And here you see the outcome. In case of DILI, there was not really a performance increase, but DILI is very complex. In case of hyperbilirubinemia, whether you include transporter information or not, does not change the performance of the model. But when you analyze descriptor importance, you see that the transporters are ranked quite high in their importance in comparison to classical physicochemical descriptors. And in cholestasis, the model significantly became better than when just using descriptors as physicochemical descriptors as feature set. So in that case, when adding transporter interaction, predicted transporter interaction patterns, the cholestasis model just became more robust. Interestingly, it was not only BSEP, it was the whole panel we needed to get a significantly better model. So this is how we currently combine transporter informatics with computational toxicology. What also very recently came out, I guess 1 or 2 weeks ago, is our study we did in EU-ToxRisk on respiratory complex 1 on mitochondrial toxicity. What we did here is we combined ligand-based and structure-based design. So structure-based design means docking of a set of compounds to the respiratory complex 1, extracting a structure-based pharmacophore model out of the docking pose, and screening a library for compounds fitting the pharmacophore models. So for compounds blocking respiratory complex 1 and thus being prone to cause mitochondrial toxicity. In parallel, we compiled the data set of around 6,000 compounds out of literature. Mitochondrial toxicity, yes, no, made a machine learning model, used the machine learning model to refine the hit list from the structure-based pharmacophore model, and finally then 3 out of 20 compounds ordered were tested in 3 different assays as being mitochondrial, toxic to mitochondria. So that would be a possibility to give you an assessment whether one of your compounds is on risk for mitochondrial toxicity. What I also promised in the abstract is a short overview. How can we include deep learning into all these complex? Here we are working, the problem we have when we would like to apply deep learning AI to toxicity prediction or to transporter informatics. Finally, the problems are twofold. One is the imbalance of data sets. What does this mean? For example, our PGP substrate models are not very good because we have an imbalance of at least 1 to 10, 100 substrates, 900 non-substrates. This is quite a challenge for classical classification models. So that's one challenge. And the other challenge is just the low number of objects. If you really would like to do deep nets, you need much more than 1,000 objects. And what we are doing here, we are going into the 3rd dimension. So we enumerate the conformational space of the ligands, and thus we create additional instances. And in contrast to SMOTI or other balancing algorithms, it's not artificial instances by just playing a bit around with the descriptor matrix. It's real instances. We just use to represent one compound in, let's say, 50 different conformations, and use conformation-dependent 3D descriptors as features. In that case, we can increase the size of the data set, plus we can balance. We just enumerate more conformations from the minority class than we do from the majority class. And how that works, and that it successfully worked for toxicity prediction, you can read up here in the paper of Jennifer Hemmerich in Journal of Cheminformatics, also just went online a few weeks ago. So at the end, I would briefly show you, let's say, or guide you through a second product Phenaris is offering. That's ToxPHACTS. ToxPHACTS is completely different to the transporter models. ToxPHACTS is not doing predictions. ToxPHACTS is analyzing data. So it's based on the basic assumption for toxicological read across. Similar structures have similar profiles. So you can expect, for example, if you look up, assume that the compound on the left is your development compound, you don't have any tox data, you do a literature search, you do a database search, you identify this compound, thalidomide, as being quite similar. You know the teratogenic potential of thalidomide, so you are immediately worried about this. So of course, the success of methods like this depend on how you define similarity and where to get the data from. It's in this case, we use a set of different similarity algorithms, not just one, focusing on let's say, substructural similarity, but a set of 5 different similarity algorithms to run our search. We are searching currently Campbell, and we are building up our internal database of compounds and their tox associations, and then we finally present the data in a sort of a heat map. So what you see here is you draw one compound, you get a list of similar compounds found in Campbell with their interaction values, their IC50 values or KI values, their, let's say, P Campbell values at the targets they have been measured on. So that's real data, that's no predictions. And if the protein, the interacting protein, is associated with a toxicity event, cardiotoxicity, cholestasis, steatosis. So we are constantly increasing this background link, target to toxicity. You get this red flag here above. And when you go a step further, then, for example, you can refine your hit list. They just show me those which are interactions which are linked with toxicity, and then when you hover over it and you click on it, you get a more decent profile. What's finally happening if you hit, for example, COX-1? What are the toxic effects you might need to consider? So this is very briefly what ToxPHACTS is offering you. Also here, Phenaris runs a twofold strategy. So a light version is available on our university website, so toxfacts.pharminfo.univ.cat, the same as the transporter models. And the more elaborated version, what means more elaborated, more similarity algorithms, more analysis details that can be accessed via the website of Phenaris or directly when you go to toxfacts.com. So finally, this was the brief overview, what we could offer to you, what we could offer to the community when it comes to transporter informatics or when it comes to toxicity prediction. And we are more than happy to answer any questions. So if you would like to get a trial license or so, please just contact us. Thank you very much.